This lesson's about equations and graphs of simple harmonic motion, and here are your objectives. So in an earlier lesson, we looked at how simple harmonic motion is related to underlying circular motion, and how if we know the angular frequency, omega, and we know the amplitude, a, of an object oscillating with simple harmonic motion, then we can find its position at any time. And we developed two relationships, this one or this one, using cos or sine, depending on whether we are starting at an extreme of motion or whether the object at time zero is at the equilibrium position. We also have seen that the angular frequency is equal to 2 pi over the period, or 2 pi times the regular frequency, and we also developed the relationship for a mass on a spring that the angular frequency is equal to the square root of the spring constant divided by the mass. So now that we've got this start at looking at the underlying math of simple harmonic motion, we're going to develop that a little bit further into equations and graphs. So I've got two columns here. Here is if we're starting at an extreme of motion at time is equal to 0, and here if we start at equilibrium at time is equal to 0. As we said in this case, the position is given by this relationship here, a cos omega t. Now remember that to go from a position time graph to velocity time to acceleration time, what we need to do is take the slope of the graph, the position time graph for example, and make it the y values of the velocity time graph, and then repeat that process for going from velocity time to acceleration time. And in calculus, that process is called taking the derivative. And so you'll learn how to do this in your math class. But again, we're going from the slope of one graph and making it the y value of the next. We do that twice here. Now, again, you'll learn how to do the trigonometric derivatives in your calculus class, but notice that there's a pattern here as we go from one to the next. We're flip-flopping between cos and sine, and we also see some negatives popping up, and we also end up with one more omega out front each time. Here 1, and now it's squared, and that's a consequence of a calculus rule called the chain rule. And you see that over here as well, flip-flopping between sine and cos, then we end up with some negatives, and another omega is added out front each time, or multiplied out front each time. So these are the equations for position, velocity, and acceleration as a function of time. Also notice that here, this part, a cos omega t, is exactly the same as this. And so we can simplify the acceleration time relationship as being negative omega squared times the position. This is the left side of this equation, and this is the right side. Similarly here in the other column, we see the same thing. A is equal to negative omega squared times the position. And so that actually is the defining equation for simple harmonic motion. Remember when we first started talking about simple harmonic motion, we said that it's defined by having an acceleration that is proportional to the displacement from equilibrium and directed back towards the equilibrium position. That's the negative sign. And we could turn that into an equation by introducing a constant of proportionality. Now we see what that constant of proportionality is. It's negative omega squared. So the defining equation for simple harmonic motion is that the acceleration is equal to negative times the angular frequency squared times the displacement from equilibrium. And remember that omega can be defined by these different ways here. And so if we know these values, we can work out omega and therefore the acceleration at any displacement from equilibrium. Also notice that from the fact that sine and cosine have maximum values of 1, no matter what the argument omega t is, the sine and cosine parts of these equations can never be more than 1. That tells us the maximum speed and the maximum acceleration. So the maximum speed can only ever be equal to the coefficients out front in that equation, so that's omega times a. Again, because omega times a can take different values, but sine omega t maxes out at positive 1. Similarly, cosine omega t maxes out at positive 1, and so the maximum magnitude, I should say magnitude, the maximum magnitude of acceleration is equal to omega squared times the amplitude. Again, now if we know the angular frequency or things above that let us work out the angular frequency and the amplitude, we now know how to find max speed and max magnitude of acceleration. Just one more note that your calculator has to be in radian mode to use these formula, because this kind of taking the derivative that borrows from calculus depends on these being in radian mode. Next, let's take a look at what this means for the graphs of simple harmonic motion with respect to time. We'll graph position time, velocity time, and acceleration time, and we'll use the equations above to think about that. So I'm just going to graph the left-hand column where I start from a position of maximum displacement. So we've seen that this has to be a cosine graph. So our cosine graph is going to look something like that. Now, if we take the derivative of that, we want to find the slope. We want to find the slope and turn it into the y value. So for example, here, the slope is 0, so that means my y value here has to be 0. Similarly, there my slope is 0, and there my slope is 0. And if I go through this and work this out, if I just ignore the equations above and think about this in terms of the slopes, I've got slopes that start at 0 and become more and more negative, and then become less negative until they become 0, then become more positive, and then more negative to 0 as well. And so working from that, I would get a graph that looks something like this. And if we check our equation above, we can see that we were looking for a negative sine graph, and this is a sine graph that's been vertically reflected in the time axis. So that works. And by a similar process, we can work out the corresponding shape of the acceleration time graph, and it's going to end up looking like a negative cosine graph. That's what the equation above tells us, and we'd also get that if we work through this kind of derivative process as well. Before we leave this, let's notice that this distance here on this graph is our amplitude A, but this distance is our maximum speed, and from the equations above, that's omega times A. This is the coefficient out in front, so it's the maximum value that the velocity time graph can take. And this distance here is omega squared A. Again, just the coefficient out in front of that negative cosine graph in the left-hand column. And notice that the position time graph and the acceleration time graph look like vertical reflections of each other. That's, of course, due to the fact that the acceleration is proportional to the negative of the displacement, so that's always going to be the case. Now, there is a vertical stretch factor down here, so we haven't labeled the y-axes, but they are going to look like vertical reflections of each other, albeit with a vertical stretch factor as well. Now let's finish up by looking at acceleration displacement graphs. So if we want to graph acceleration versus displacement, again, acceleration is proportional to the negative of displacement in simple harmonic motion, and now we've seen that acceleration is equal to the negative of the angular frequency squared multiplied by the displacement. So in this graph, we should have a straight line going through the origin with negative slope. And the slope of this graph is equal to negative omega squared. We could change this and make this a force versus displacement graph, and if it were force versus displacement, we would need to multiply both sides here by mass, because mass times acceleration, that's equal to force. So I would get negative mass times omega squared times x, and in this case, the slope would be equal to negative mass times omega squared. So let's look at equations and graphs of simple harmonic motion.